this class, we'll talk about structural sensitivity analysis. So sometimes we need to add a new variable in the linear programming problem. This happens when, for example, a company wants to produce a new product. In this case, we will consider if producing this new product will be profitable or not. That is, we'll find an optimal solution with the new variable. The convenient way to deal with this is to treat it as the non-basic variable case we discussed earlier. This is done by pretending that the new variable xj actually was in the original model with all its coefficients equal to 0, and that xj is a non-basic variable in the current BF solution. In particular, all we have to do is to check whether the current solution still is optimal, is to check whether the complementary basic solution y star satisfies one new dual constraint that corresponds to the new variable in the primal problem. Let's look at an example. If we have this problem of maximizing Z in the matrix form, and we can obtain its final simplex tabular. Now consider that we want to introduce a new variable x6 with its coefficients listed as here. Well, again, first coefficient is the coefficient of x6 in the objective function, and the rest are the coefficients in the constraints. Practically, we can consider C6 as the profit of producing product 6, and then these A's are the materials it will use. And then after we want to produce a new product, how the optimal solution will change. So first, we recall that the idea is still the same as before. We treat x6 as a non-basic variable. So if we introduce this new column into our final simplex tabular, we need to change the coefficient of all this this column. So for the non-basic variables, our formula is as before. The first coefficient of xj in the final equation 0 is y star aj bar minus cj. And then the coefficient of xj in the rest of the equations is s star times aj bar. So by applying these formulas, we say, well, the coefficient in the first equation 0 will be y star aj bar, which is y star, again, reading from the top, the values of the slack variables here, 0, 0, 5 halves, times aj bar, the column vector in the constraint, so 2, 1, 2, minus cj, 6, and then we find this is negative 1. Correspondingly, we say the coefficients of x6 in the rest of the column will be s star, the matrix of the slack variables, times aj bar, again, this 2, 1, 2, the new column vector. And then we obtain the resulting column vector. So with these vectors introduced, we say that all we're going to do here is to add a new column as the variable we introduced and add all the values we calculated for this column. After we have this, again, we repeat the same procedure as before. The first column, the first row, equation 0, contains a negative value, so it doesn't pass the optimality test. Then this is the pivot column, and x6 is entering as the basic variable. And then we do the minimum ratio test, find out that this 2 has the minimum ratio, and then x3 is the leaving basic variable. After this, we are going to make this column unit by using Gaussian eliminations. So once we do the Gaussian elimination correctly, we can figure out that after one iteration, we obtain the optimal solution because now all the coefficients in equation 0 are non-negative. And then on the right, all the values are also positive. So in this case, we say if we want to add a new variable x6, then the new basic optimal solution will be x6, x2, x4 equal to 2, 7, 8. And then our new value of the objective function will be 47. This is actually an improvement from 45. Okay, so from this, on the other hand, we can also test optimal from the dual problem. The dual problem is equivalent to adding a new constraint. So since this is our new coefficients we add to our variable, and then the dual problem is when we do the multiply these y's, y1, y2, y3, and then y1, y2, y3 times 2, 1, 2 is bigger than or equal to the coefficient in the objective function 6. So this is the new constraint in the dual problem we add. So with this constraint, we say that our original solutions to the dual problem, the values x1 through x3, 0, 0, 5 halves. So these values, when we substitute into the new constraint, we can see that the inequality does not hold. In other words, in this case, this solution is not optimal, and then we need to apply simplex method or the dual simplex method to obtain another optimal solution. So in general, if we have this Cj star minus Cj bar bigger than or equal to 0, the current solution is optimal. In other words, the new product should not be produced. On the other hand, if this value is less than 0, then the current solution is not optimal, and we need to apply simplex method to seek for a new optimal solution. And we should produce this new product to earn a better profit, because the coefficient of the objective function less than 0 means improving the value of that variable will improve the value of our objective function. Next, we talk about the case of introducing a new constraint. In some situations, the materials may be insured after a period, and in this case, we need to change our plan by introducing new constraint. To see if the current optimal solution would be affected by new constraint, all we have to do is to check directly whether the optimal solution satisfies the constraint. If it does, then it will still be feasible solution. Again, let's look at an example. For example, if we have this final simplex tabular, and now we add a new constraint of 2x1 plus 3x2 less than or equal to 24. And then how will this constraint affect our model? Put the optimal solution to test the constraint. We can see that this is our optimal solution. And then x1 equals 0 is non-basic. Optimal solution in our constraint, we can see the constraint is not satisfied. In other words, our solution is actually now super optimal in this case. So we need to do something to change to make it a solution, an optimal solution. So in order to do that, again, since this is a less than or equal to an inequality, we first want to change it to the standard form by introducing a slack variable. So we introduce a new variable x6 and have an equation as a new constraint. With this new constraint, all we are going to do is to directly add our constraint into the tabular directly. So we add a new variable x6. x6 does not appear in all the previous equations. It only appears in our last constraint. So we say this is the new constraint, and the coefficient of x6 in all these equations will be 0, 0, 0, 0, and 1. On the other hand, the coefficients of x1 and x2 are 2 and 3 respectively, reading by rows. So this is our new simplex tabular. All we did is to introduce a new constraint and add this constraint to our final simplex tabular. So find out the coefficients of all the variables and make this new tabular. After we make this new tabular, we can see that, well, our basic variables now are x3, x2, x4, and x6. x3 is okay, x4 is okay, x6 is okay. However, for x2, its column has one more coefficient that should not be there. Now the column of x2 is not in the proper form. So again, we play the same game. In order to check whether this is an optimal solution or to start the simplex method or the dual simplex method, we need to first do the Gaussian elimination to make this column proper. So we can easily multiply 3 to this row and then subtract it to the last row to get rid of that 3. And then after we make these modifications, we have a proper simplex tabular. And then in this simplex tabular, we have all the corresponding basic variables and non-basic variables listed. Now, if we examine this tabular, we can see that now the top row, equation 0, has all the coefficients non-negative, so it passed the optimality test. However, if we look at the right side, we can see that one of the basic variables, x6 in this case, is actually negative. So this solution is not feasible. It's not feasible, so we know we're going to apply the dual simplex method to find out an optimal solution. In this case, we say this is the only negative value, so x6 is the leaving basic variable. And then apply the minimum ratio test, we can find out that these actually have a minimum ratio. So in this case, we say x5 is the entering basic variable and x6 is the leaving basic variable. After we have these concepts, all we are going to do now again is to do the Gaussian elimination to make this column a unit column in the proper form 0, 0, 0, 0, 1. So if we do the Gaussian elimination correctly, we would obtain a table, and in this table again we check all the coefficients in equation 0 are non-negative. It passed optimality test. All the basic variables on the right side are positive, so it's a feasible solution. It's feasible and then it's optimal. So with this optimal solution, we can read directly about the values of the basic variables and our objective function. So we say if the new constraint does eliminate the current optimal solution, then introduce this constraint into the final simplex tabular just as if this were the initial tabular. And then the usual additional variable is designated to be the basic variable for this new row. The conversion to proper form from Gaussian elimination is applied next. And then the reoptimization step is applied in the usual way, as we've seen from the example.